The development team has submitted a ticket for a web application that is crashing due to high CPU utilization. The network admin has suggested creating a managed instance group to handle the load. Which suggested configuration below could solve the problem? A. Create a managed instance group with an auto-scaling policy based on load balancing serving capacity. B. Create a managed instance group with a cluster autoscaler with a fixed minimum and a maximum number of instances. C. Create a managed instance group with an auto-healing policy that attempts to recreate the crashed instance. D. Create a managed instance group with an auto-scaling policy based on CPU utilization. Alright, to figure out the right answer, let's break down the problem. First, we need to understand the root cause. The problem is clearly stated as the application crashing due to high CPU utilization. Next, let's discuss the objective. A solution is needed to handle the load and prevent virtual machines from crashing due to CPU overload. This requires a proactive mechanism to add more resources, or virtual machines, when the CPU load starts to increase. Okay, with that understanding, let's evaluate each of the options one by one. Let's look at option A. This option is incorrect because, while it's true that high traffic often leads to high CPU, scaling based on the CPU metric itself is a much more direct and precise approach. Since the core issue is CPU, that's what we should be tracking and acting on. Now for option B. This one is also incorrect. Cluster Autoscaler is the specific term for Google Kubernetes Engine, or GKE, which is used to manage nodes in a container cluster. Our problem talks about a standard managed instance group, so this option is irrelevant to our scenario. Moving on to option C. This is incorrect as well. Auto-healing is a reactive mechanism, not a proactive one. It only kicks in after a crash has already happened to replace the failed instance. What we need is a solution that prevents the crash from happening in the first place. This brings us to option D. This is the most direct and effective solution. By setting up an auto-scaling policy based on CPU utilization, for example, keeping the average CPU usage at 60%, the system will automatically add new virtual machines as the load increases. This distributes the workload across more machines, reducing the CPU load on each individual instance and preventing them from becoming overloaded and crashing. So, after analyzing all the options, we can conclude that the correct answer is D. Create a managed instance group with an auto-scaling policy based on CPU utilization. Question 2. An application development team believes their current logging tool will not meet their needs for their new cloud-based product. They want a better tool to capture errors and help them analyze their historical log data. You want to help them find a solution that meets their needs. What should you do? A. Direct them to download and install the Google Stackdriver logging agent. B. Send them a list of online resources about logging best practices. C. Help them define their requirements and assess viable logging tools. D. Help them upgrade their current tool to take advantage of any new features. Okay, to analyze this scenario, let's first understand the role you're playing. In this question, you are acting as a consultant or an architect. The situation is that a development team needs a new logging tool, but hasn't decided on one yet, and your objective is to help them find the best possible solution. The key takeaway here is that the correct approach for a consultant isn't to jump to a specific solution immediately. Instead, you should always start by deeply understanding the team's problem and their specific requirements. With that context in mind, let's go through each of the options. Looking at option A, this would be a premature action. It suggests a specific solution, the cloud logging agent, without first understanding the team's full requirements. While cloud logging is a powerful option, it might not be the best fit for their specific needs, budget, or other integration requirements. Next, option B. This approach is too passive and isn't genuinely helpful. The team is looking for direct guidance. Just sending them a list of documents to read on their own won't bring them any closer to selecting the right tool. Now let's look at option C. This represents the standard and most effective process for consulting and architectural design. The first part, help them define their requirements, is the most critical first step. This means clarifying detailed needs such as what kind of logs they need to analyze, how long the logs need to be stored, their requirements for alerting speed, their budget, and any other specific features they need. The second part, assess viable logging tools, comes next. Once you have a clear set of requirements, you can objectively evaluate different tools, including cloud logging and others, to see which one best meets those needs. Finally, option D is incorrect because the team has already stated that their current tool will not meet their needs. Focusing only on upgrading the old tool ignores their assessment and likely won't solve the root problem. Evaluating an upgraded version of the old tool should be part of the assessment process described in option C, not the first and only action taken. Therefore, based on this analysis, the best course of action is C. Help them define their requirements and assess viable logging tools. Question 3. There is one application that has been utilizing a lot of bandwidth by sending out large packets. This particular app attempts to control the TCP window size so that it can maximize its own performance to the detriment of other services running on the same virtual machine. Which Linux tunable below would you adjust to set the maximum OS send buffer size for all connections? net.core.rem_max. B. net.core.mem_max. C. net.ipv4.tcp_mem. D. net.ipv4.tcp_mem. Alright, to break this question down, let's first analyze the core problem. The situation is that a single application is hogging bandwidth by trying to maximize its own send buffer size. Our objective is to adjust a Linux operating system parameter to set a maximum limit for the send buffer size. This limit needs to apply to all connections to prevent this one application from causing problems for other services. To solve this, you need to understand some key Linux networking parameters, specifically the difference between core and IPv4.TCP settings, and the difference between rem for receive memory and mem for write or send memory. With that knowledge in mind, let's examine the options. Option A, net.core.rem_max, is incorrect. The R in rem stands for receive. This parameter adjusts the maximum receive buffer size. The problem requires us to adjust the send buffer. Now, let's look at option B, net.core.mem_max. This looks very promising. Let's break it down. The net.core prefix means it applies at the kernel core level, affecting all network protocols. The W in mem stands for write or send, and max sets the hard maximum limit for this send buffer. Any application that tries to request a send buffer larger than this value will be capped. This directly addresses our problem. Moving on to option C, net.ipv4.tcp_mem. This is incorrect for two reasons. First, like option A, it deals with the receive buffer, not the send buffer. Second, the net.ipv4.tcp prefix means it only applies to TCP connections, not all connections as the question requires. Finally, we have option D, net.ipv4.tcp_mem. This option is close, but still incorrect. While mem correctly refers to the send buffer, the net.ipv4.tcp prefix limits this setting only to TCP connections. The requirement is to set a global limit for all connections. Therefore, the net.core parameter from option B is the more comprehensive and correct answer. In fact, net.core.mem_max acts as the absolute ceiling for net.ipv4 anyway. So, after reviewing all the parameters, the correct answer is B, net.core.mem_max. Question 4. A newsfeed web service has the following code running on Google App Engine. During peak load, users report that they can see news articles they have already viewed. What is the most likely cause of this problem? A. The session variable is local to just a single instance. B. The session variable is being overwritten in Cloud Data Store. C. The URL of the API needs to be modified to prevent caching. D. The HTTP expires header needs to be set to -1 to stop caching. Okay, to get to the bottom of this, let's analyze the problem in detail. First, let's analyze the application code. The problem description implies that the application is storing the user's viewed articles in a global, in-memory variable, likely called sessions. Next, let's analyze the environment. Google App Engine is a platform that scales automatically. This means that during peak load, it will launch new instances to handle all the incoming requests. So what is the root cause? The sessions variable is local to each individual instance. It is not shared across the different instances. Imagine a user makes their first request and is sent by the load balancer to instance A. Their session data showing which articles they've seen is stored right there in the memory of instance A. But when they make a second request, the load balancer might send them to a brand new instance B. Instance B has no knowledge of the session data created on instance A. As a result, it treats the user as if they're brand new and sends them the same old articles again. With this root cause in mind, let's evaluate our options. Starting with option A. This is precisely the cause of the problem we just described. The in-memory sessions variable isn't synchronized across the different App Engine instances. Storing application state in the memory of a single instance is a classic architectural mistake when working on horizontally scaling platforms. Option B is incorrect. Based on the problem description, the code isn't using Cloud Data Store at all. All of the session management is happening right in the application's memory. Option C is also incorrect. The issue here isn't related to client-side or CDN caching. This is a server-side logic problem. The server itself is generating the wrong content because it has lost the user's state information. And finally, option D is incorrect for the same reason as option C. Changing HTTP headers only affects caching. The root of the problem is improper state management on the server side. So, to wrap it all up, the most likely cause of this problem is the session variable is local to just a single instance. Question 5. Your company has recently acquired another company operating in Spain to expand your market in Europe. You have to integrate their legacy systems into your company's systems. Your company uses GCP as the primary cloud to manage your applications. Assuming your team is taking this opportunity to modernize parts of the legacy system, what is the best way to integrate this system into your company's systems? A. Containerize the legacy applications using GKE and run them on the on-prem instances. Use Anthos for managing the applications. B. Create a snapshot of the legacy systems and run them on compute instances on GCP. C. Containerize the legacy applications using GKE and run the GKE instances on GCP. D. Use a transfer appliance to securely ship the data from on-prem systems to GCP. Alright, to break this question down, let's first analyze the key details from the problem description. First, the input data. The newly acquired company has legacy systems, which implies they are currently running on-premise. Your company uses GCP as its primary cloud platform, so the context is a hybrid environment that includes both on-premise infrastructure and GCP. Now for the requirements. The first keyword is integrate. We need a solution that can connect and provide unified management for both the old on-premise systems and the new systems on GCP. The second keyword, and this is the most important one, is modernize. The solution shouldn't be a simple lift and shift migration. It must involve improving and upgrading the system's architecture. Therefore, the ideal solution must meet both of these criteria. It has to upgrade the application architecture and provide management capabilities for a hybrid environment. With these requirements in mind, let's evaluate our options. Let's start with option A. This is a very strong candidate. First, it meets the modernize requirement. Containerizing is a common and effective method for modernizing applications, making them more flexible and easier to manage. Second, it meets the integrate requirement. Anthos is Google's platform for managing hybrid and multi-cloud environments. It lets you manage Kubernetes clusters, whether they're running on GCP or on-premise. This approach is also highly practical. It suggests a phased approach. First, modernize the application in place by containerizing it on its existing hardware. Then you use Anthos for unified management across both your newly modernized on-prem app and your existing GCP apps. This is the most comprehensive solution. Now let's look at option B. This is incorrect. This describes a classic lift and shift migration. You're simply making a copy of the old server and running it on a compute engine instance in GCP. This method completely ignores the modernize requirement. The system is still a legacy system, just running in a different location. Option C does involve modernization through containerization, which is a plus. However, it's not the best answer in this context. Migrating the entire containerized application to GCP immediately could be very disruptive and risky, especially for a legacy system. More importantly, it doesn't mention how to integrate and manage the environment during the transition phase. Option A, with Anthos, provides a much clearer and more flexible hybrid management solution. Finally, Option D is incorrect because Transfer Appliance is a service specifically for migrating large amounts of data, not applications or systems. This option only addresses a tiny part of the problem and completely fails to address the main requirements of integrating and modernizing the application. Therefore, after a full analysis, the best way to integrate and modernize this system is to containerize the legacy applications using GKE and run them on the on-prem instances, and use Anthos for managing the applications. Question 6. The operations manager asks you for a list of recommended practices that she should consider when migrating a J2EE application to the cloud. Which 3 practices should you recommend? Choose 3. A. Port the application code to run on Google App Engine. B. Integrate Cloud Dataflow into the application to capture real-time metrics. C. Instrument the application with a monitoring tool like Stackdriver Debugger. D. Select an automation framework to reliably provision the cloud infrastructure. E. Deploy a continuous integration tool with automated testing in a staging environment. F. Migrate from MySQL to a managed NoSQL database like Google Cloud Data Store or Bigtable. Alright, this question asks us to identify 3 recommended practices for migrating a J2EE application to the cloud. Let's analyze the key concepts before diving into the options. First, what are we migrating? It's a J2EE application. These are typically large, complex, enterprise-level Java applications. The goal is a cloud migration, and we need to provide a list of recommended practices. This implies we're looking for modern principles that offer long-term value, not just simple migration tactics. So, our task is to choose the 3 best practices that cover the critical aspects of a cloud migration project. Ideally, these practices should touch on the application runtime, infrastructure management, and the development and deployment process. With that framework in mind, let's evaluate each option. Let's start with A. This is a good practice. Google App Engine is a platform as a service or PaaS. Porting an application to a PaaS platform is a common and highly recommended modernization strategy. It abstracts away the underlying infrastructure, freeing the development team from managing things like scaling and OS patching, so they can focus entirely on the application code. Now for option B. This is incorrect. Cloud Dataflow is a powerful service for large-scale batch and stream data processing, like for ETL pipelines or data analytics. Using it just to capture application performance metrics is overkill and not what the tool is designed for. The specialized tool for that is cloud monitoring. Option C is also incorrect. While application monitoring is critical, Cloud Debugger is a specialized tool for debugging live applications without stopping them. It's not the primary tool for monitoring performance metrics. Compared to the other choices, this isn't a foundational practice for an entire migration project. Let's look at option D. This is another excellent practice. This refers to the principle of infrastructure as code, or IAC, which is a core concept of DevOps and cloud computing. Using tools like Terraform or Cloud Deployment Manager to define infrastructure in code ensures that environments are created consistently, reliably, and repeatably. This is a must-have for any serious cloud project. Now for option E. This is also a correct and critical practice. This describes setting up a CI/CD pipeline, which stands for continuous integration and continuous deployment. Automating the build, test, and deployment process is one of the most important practices in modern software development. Adopting CI/CD during a cloud migration helps increase release velocity and improve quality. Finally, let's look at option F. This is incorrect as a general recommendation. Traditional J2EE applications are often built on relational SQL databases like MySQL. Migrating from SQL to NoSQL isn't a simple task. It's a major re-architecture. The application's data model may not even be suitable for a NoSQL database. While moving to a managed database like Cloud SQL would be a good practice, a complete switch from SQL to NoSQL is not a universally recommended practice for every J2EE application. So, to summarize, the 3 recommended practices we should choose are A, D, and E. Question 7. A startup in the decentralized finance space provides portfolio management services for customers holding digital assets. In order to manage the digital assets, they take custody of their customers' private keys, which are very sensitive and prone to hacking. They plan to use the private keys of high-value assets only when required and store them offline in their on-premise systems. They use GCP as their primary infrastructure and would like to know how to access and update the private keys securely only when required. What is the best way to achieve this? Choose 3. Create a VM in a separate VPC and use it to temporarily store the private keys. Create a peering connection with the main VPC to update or access the private keys. B. Store the private keys on-premise and copy them to the VM through a cloud VPN. C. Copy the updated private keys back to the on-prem system and delete the VM instance. D. Connect the on-prem system to the main VPC through a cloud VPN. Okay, this question is about creating a secure workflow for handling very sensitive data. Let's break down the requirements before we look at the options. First, the context. The company is in the DeFi space, handling customer private keys, which are extremely sensitive. Their strategy is to keep these keys offline in an on-premise system, which is known as cold storage, and only bring them into a hot, online environment on GCP when absolutely necessary for transactions. So, the core task is to find a secure, 3-step process to bring these keys from cold storage to the hot environment, use them, and then return them safely. This process must prioritize security, isolation, and be temporary. The key here is that we are looking for 3 steps that, together, form one complete secure workflow. Let's see how the options fit together. Options A, B, and C, when combined, create exactly this kind of complete and highly secure process. Let's walk through it step by step. Step 1 is option A. This sets up an extremely isolated environment for handling the sensitive data. Creating a separate VPC instead of using the main one significantly reduces the attack surface. The virtual machine holding the private keys won't be exposed to the other applications and traffic in the main VPC. VPC peering then provides a controlled, private connection to the main VPC if needed, without exposing the sensitive VM. Step 2 is option B. This addresses the secure connection requirement. The data starts on-premise. To move it to the temporary VM we just created in Step A, we need a secure tunnel. A cloud VPN provides an encrypted connection between the on-premise network and the GCP VPC, ensuring the private keys are not exposed during transit. Step 3 is option C. This completes the workflow by ensuring the process is temporary and leaves no trace behind. After the transaction is done, the private keys are securely copied back to the cold storage on-premise via the cloud VPN. Then, the entire virtual machine is destroyed. This ensures no sensitive data is left behind on the cloud, minimizing the risk exposure time to an absolute minimum. Now let's look at why option D is incorrect on its own. This option suggests connecting the on-premise system directly to the main VPC. This goes against the principle of isolation we established in Step A. It would expose the cold storage system to the entire main application network, which has a much larger attack surface. The connection should only be made to the small, separate, and temporary VPC to ensure maximum security. So, the 3 options that together form the best and most secure process are A, B, and C. Question 8. Your company plans to migrate a multi-petabyte data set to the cloud. The data set must be available 24 hours a day. Your business analysts have experience only with a SQL interface. How should you store the data to optimize it for ease of analysis? Load data into Google BigQuery. B. Insert data into Google Cloud SQL. C. Put flat files into Google Cloud Storage. D. Stream data into Google Cloud Data Store. Okay, let's break down this question. We need to find the best way to store a massive dataset to make it easy for business analysts to work with. First, Let's look at the key pieces of input data. The data size is multi-petabyte. This is a huge amount of data and is the most important factor in our decision. The data must also be available 24 hours a day. Crucially, the users are business analysts who are only familiar with a SQL interface. And the main goal is to optimize the data for ease of analysis. This tells us the primary purpose is data analytics, also known as OLAP, not transactional processing or OLTP. So, putting it all together, the solution must be able to handle petabyte-scale data, provide a SQL interface, be optimized for analytics, and be highly available. With those requirements in mind, let's go through the options. Let's start with option A, load data into Google BigQuery. BigQuery is Google's serverless data warehouse, and it's specifically designed to solve this exact type of problem. First, it scales to handle and query petabytes of data efficiently. Second, it uses a standard SQL dialect, which perfectly matches the analyst's skill set. And third, as an OLAP system, it's built to run complex analytical queries on large datasets with incredible speed. BigQuery perfectly meets all the requirements of the question. Now for option B, insert data into Google Cloud SQL. This is incorrect. Cloud SQL is a managed service for relational databases like MySQL or PostgreSQL. These systems are designed for transactional processing or OLTP and simply cannot handle petabyte-scale data effectively. Cloud SQL storage limit is in the tens of terabytes, which is far, far smaller than a petabyte. Let's look at option C. Put flat files into Google Cloud Storage. This is also incorrect. While Google Cloud Storage can certainly store petabytes of data, it is an object storage service. By itself, it does not offer a SQL interface for direct querying. Although you can query data in GCS using BigQuery, GCS alone does not meet the requirement of ease of analysis using SQL. Finally, option D, stream data into Google Cloud Data Store. This is incorrect. Cloud Data Store, which is now part of Firestore, is a NoSQL database. This means it doesn't use a standard SQL interface, which violates the user skill requirement. Furthermore, it's designed for transactional web and mobile applications, not for running complex analytical queries on massive datasets. Therefore, the only solution that satisfies all the conditions is a load data into Google BigQuery. Question 9. A development team has launched a vital application on a regional managed instance group that must have nearly zero downtime. To ensure high availability, you now have to configure a global load balancer to direct HTTP traffic across multiple zones. After configuring the backend, then the front end of the load balancer, you click Review and Finalize. Assuming you have configured the load balancer correctly, what backend settings do you see upon review? A. The backend service is Web App Backend. The endpoint protocol is HTTP. The health check is Web App Load Balancer Check. The instance group is Load Balancing Web App Group. B. The backend service is Web App Backend. The endpoint protocol is TCP. The health check is Load Balancing Web App Group. The instance group is Web App Load Balancer Check. C. The backend service is Web App Backend. The endpoint protocol is HTTP. The health check is Load Balancing Web App Group. The instance group is Web App Load Balancer Check. D. The backend service is Web App Backend. The endpoint protocol is TCP. The health check is Web App Load Balancer Check. The instance group is Load Balancing Web App Group. Okay, this question tests our knowledge of how a global external HTTP load balancer is configured in Google Cloud. Let's break down the key details from the prompt. First, we're dealing with a vital application that requires high availability. We're setting up a global load balancer, and the traffic type is HTTP. This is the most important keyword in the entire question. The backend for this load balancer is a regional managed instance group. So, our task is to identify the correct backend configuration settings as they would appear on the Review and Finalize screen. This includes the protocol, the backend service, the instance group, and the health check. With that in mind, let's analyze the options. Let's start with option A. The core detail here is that the endpoint protocol is HTTP. This is fundamentally correct. The question explicitly states we're directing HTTP traffic, so the protocol between the load balancer and the backend instances must be HTTP. Furthermore, the naming convention here is logical. A load balancer has a backend service which points to one or more instance groups, and it uses a health check to monitor the VMs in that group. The names assigned in this option make perfect sense for their roles. Now let's look at option B. This is incorrect due to a fundamental error. The protocol is set to TCP. A global external HTTP load balancer is a layer 7 load balancer that operates at the application layer. Therefore, the protocol must be configured as HTTP or HTTPS. TCP is used for layer 4 load balancers. On top of that, the names for the health check and the instance group are swapped, which doesn't make logical sense. Moving on to option C. While the protocol here is correctly set to HTTP, the names for the health check and the instance group have been swapped. The name Load Balancing Web App Group clearly sounds like a group of virtual machines, not a health check rule. So this is also incorrect. Finally, option D is incorrect for the same reason as option B. The protocol is listed as TCP, which is wrong for a global HTTP load balancer. Even though the other names are assigned correctly, this protocol error makes the entire option invalid. Therefore, after reviewing all the settings, the only correct and logically named configuration is A. The backend service is Web App Backend. The endpoint protocol is HTTP. The health check is Web App Load Balancer Check. And the instance group is Load Balancing Web App Group. Question 10. Your company has decided to make a major revision of their API in order to create better experiences for their developers. They need to keep the old version of the API available and deployable, while allowing new customers and testers to try out the new API. They want to keep the same SSL and DNS records in place to serve both APIs. What should they do? A. Configure a new load balancer for the new version of the API. B. Reconfigure old clients to use a new endpoint for the new API. C. Have the old API forward traffic to the new API based on the path. D. Use separate backend pools for each API path behind the load balancer. Okay, let's break down this common API versioning problem to find the best solution. First, the scenario. The company is releasing a major revision of an API, which means they'll have two versions, the old and the new, running in parallel. A key requirement is that both versions must be available at the same time. Another critical requirement is to keep the same SSL and DNS records. This means both API versions must be accessible through the same domain name. So, our task is to find a solution that allows a single entry point to route traffic to different backend services. The most common way to do this is by using different URL paths. For instance, api.company.com/v1, https://www.google.com/search?markq=, https://api.company.com/v1 for the old API and /v2 for the new one. The solution must be able to leverage this capability. With these requirements clear, let's evaluate the options. Option A is incorrect. A new load balancer would get a new IP address. This would require a new DNS record to point to it, which violates the requirement to keep the DNS records the same. Option B is also incorrect. The question states that the old version must remain available. This option implies forcing old clients to migrate, which contradicts the requirements. Besides, the term new endpoint is vague and doesn't describe a clear routing implementation. Moving on to option C. This is an inefficient and brittle approach. It creates an unnecessary dependency and a single point of failure. All traffic would have to hit the old API service first, which would then forward traffic to the new API. This adds latency and tightly couples the two versions. The load balancer layer is the proper place to handle this routing logic, not the application layer. This brings us to option D, which is the standard and most effective way to solve this problem. Modern load balancers like the Google Cloud External HTTP/S load balancer fully support path-based routing. Here's how it works. You configure a single load balancer with one frontend. That means one IP address and one SSL certificate. Then, you create routing rules to direct traffic based on the URL path. traffic for the path/v1 gets sent to one backend pool running the old API code. Meanwhile, traffic for the path/v2 gets sent to a different backend pool running the new API code. This approach meets all the requirements perfectly. So, after analyzing all the options, the correct solution is D. Use separate backend pools for each API path behind the load balancer. Question 11. When you use Google Cloud Code to integrate Anthos with an IDE, blank uses your local Docker installation to manage a single Kubernetes cluster on your development machine. OpenShift. B. OpenStack. C. Minikube. D. Scaffold. Alright, to answer this question correctly, we need to understand what's happening behind the scenes when you use Google Cloud Code for local Kubernetes development. Let's break down the input data. The main tool here is Google Cloud Code, which is an extension for IDEs. The goal is to develop for Anthos and Kubernetes right on a local developer machine. The question asks for the specific tool that uses your local Docker installation to create and manage a single Kubernetes cluster for this purpose. So, the core task is to identify the tool responsible for creating that local cluster environment. With that in mind, let's evaluate our options. First, option A, OpenShift. This is incorrect. OpenShift is a full-scale, enterprise-grade container platform from Red Hat. It's a complete Kubernetes distribution, not a lightweight tool for running a single cluster on a developer's laptop. Next, option B, OpenStack. This is also incorrect. OpenStack is an open-source platform for building private clouds. It manages large-scale resources like virtual machines, storage, and networking, and is completely unrelated to running a local Kubernetes cluster. Now, let's look at option D, Scaffold. This is a tricky one because Google Cloud Code does use Scaffold, but for a different purpose. Scaffold handles the development workflow. It automates the cycle of detecting code changes, building a container image, pushing that image to a registry, and deploying it to a Kubernetes cluster. Scaffold deploys to a cluster. It doesn't create or manage the cluster itself. This leaves us with option C, Minikube. This is the correct answer. Minikube is the official and most popular tool designed for this exact purpose. Its main function is to help developers quickly set up a simple, local, single-node Kubernetes cluster on their personal computer. Minikube uses various drivers to run this cluster, with one of the most common being the local Docker installation. Google Cloud Code integrates with and uses Minikube to provide that seamless local development and debugging experience. Therefore, the tool that creates and manages the local Kubernetes cluster is C, Minikube. Question 12. You need to reduce the number of unplanned rollbacks of erroneous production deployments in your company's web hosting platform. Improvements to the QA and test processes accomplished an 80% reduction. Which additional two approaches can you take to further reduce the rollbacks? Choose 2. Introduce a green-blue deployment model. B. Replace the QA environment with canary releases. C. Fragment the monolithic platform into microservices. D. Reduce the platform's dependency on relational database systems. E. Replace the platform's relational database systems with a NoSQL database. Alright, let's break down this scenario. The core problem is that there are still too many rollbacks due to deployment errors, even after the QA process was improved. Our goal is to find 2 additional methods that can help reduce this problem even further. This means we should focus on deployment strategies and application architecture, since the testing process has already been addressed. With that in mind, let's evaluate our options. First, let's look at option A. Introduce a green-blue deployment model. This is a correct answer. Blue-green is a deployment strategy specifically designed to minimize risk. It works by maintaining 2 identical production environments, blue for the current version and green for the new version. You can deploy the new version to the green environment and test it thoroughly without impacting any users. Once you're confident, you simply switch the traffic over to green. If any problems arise, switching the traffic back to the stable blue environment is nearly instantaneous, eliminating complex rollback procedures. Now for option B, replace the QA environment with canary releases. This is incorrect because a canary release is a production deployment strategy, not a replacement for a QA environment. A QA environment is for testing before a release goes to production. A canary release means you deploy the new version to a small subset of real users in production. The idea of replacing the QA environment is a bad practice, as it removes a critical testing step before users are exposed to the new code. Let's move on to option C. Fragment the monolithic platform into microservices. This is also a correct answer. Moving from a monolithic architecture to microservices significantly reduces the blast radius of a failure. In a monolith, a small bug in one feature can bring down the entire system, forcing a full rollback. With microservices, you can deploy and update services independently. If one service fails, only that service is affected, and you only need to roll back that single small service, not the entire platform. Next, option D, reduce the platform's dependency on relational database systems. This is incorrect because it's too vague. Reducing dependency on a relational database doesn't automatically mean the system will be more reliable or have fewer deployment errors. The choice of database technology depends on the data's needs and isn't a direct strategy for reducing deployment risk. Finally, option E, replace the platform's relational database systems with a NoSQL database. This is incorrect. Replacing a relational database with NoSQL is a massive architectural change that introduces a lot of risk on its own. There's no guarantee this would reduce rollbacks. In fact, such a complex database migration project would likely increase the number of errors in the short term. The root of the problem is the deployment process and application architecture, not the database technology. So, to conclude, the two best additional approaches to reduce rollbacks are A, introducing a blue-green deployment model, and C, fragmenting the monolithic platform into microservices. Question 13. A financial service provider runs their GCP infrastructure in the London region. They promise high service levels to their customers and cannot risk regional unavailability. The head of IT wants to have a disaster recovery plan for their Cloud SQL instances in case the region fails or becomes unavailable. Regulation requires that they keep the data in the European region. What are the steps for a complete disaster recovery plan that will give them a near-zero recovery point objective? Choose 3. A. Create cross-region RED replicas of the SQL instances in Belgium. If failover is required, make the cross-region RED replica the primary. B. Create a new standby instance in a different zone in Belgium. C. Create cross-region RED replicas of the SQL instances in South Carolina. If failover is required, make the cross-region RED replica the primary. D. Create a new cross-region replica in Frankfurt and attach it to the primary instance. Alright, this is a complex disaster recovery scenario, so let's break down the key requirements before we look at the options. First, the context. The service is Cloud SQL running in London. The main problem we need to solve is creating a disaster recovery, or DR, plan in case the entire London region fails. A critical constraint is that the data must legally remain within Europe. And finally, the recovery point objective, or RPO, needs to be near zero, which means we need a solution with minimal data loss. Our task is to build a complete DR plan, which often involves multiple layers of protection to meet such strict requirements. With that in mind, let's evaluate our options. Let's start with option A. This is a correct and essential step. It describes the core of any good DR plan. Creating a cross-region RED replica in another European location, like Belgium, ensures the data is safe if London goes down. More importantly, it includes the actionable step of promoting the replica to become the new primary during a failover. This makes the plan executable and directly addresses the regional failure problem while complying with data residency rules. Now for option B. This is also a correct step because it adds a layer of high availability, or HA. A standby instance in a different zone protects the system from a single zone failure. While the main question is about regional DR, a truly complete plan for a critical financial service would almost certainly include HA as the first line of defense. We can interpret this as setting up the DR site in Belgium to be highly available from the start, ready to take over with high reliability after a failover. Let's look at option C. This is immediately incorrect. It directly violates the legal requirement to keep data within Europe. South Carolina is in the United States, so this option is not viable. Finally, option D. This is also a correct step because it provides an additional layer of redundancy to the DR plan. For a financial service that cannot risk regional unavailability, having multiple DR locations, in this case both Belgium and Frankfurt, offers the highest possible level of resilience. If a catastrophic event were to impact both the primary London region and the first DR site in Belgium simultaneously, the company would still have the option to fail over to the second DR site in Frankfurt. So, when we put it all together, the 3 steps that form a complete and robust disaster recovery plan are A, B, and D. Question 14. To reduce costs, the Director of Engineering has required all developers to move their development infrastructure resources from on-premises virtual machines to Google Cloud Platform. These resources go through multiple start/stop events during the day and require state to persist. You have been asked to design the process of running a development environment in Google Cloud while providing cost visibility to the finance department. Which 2 steps should you take? Choose 2. A. Use the No Auto Delete flag on all persistent disks and stop the VM. B. Use the Auto Delete flag on all persistent disks and terminate the VM. C. Apply a VM CPU utilization label and include it in the BigQuery billing export. D. Use Google BigQuery billing export and labels to associate costs to groups. E. Store all state into local SSD, snapshot the persistent disks, and terminate the VM. F. Store all state in Google Cloud Storage, snapshot the persistent disks, and terminate the VM. Okay, this question has 2 distinct parts we need to solve. First, how to manage the virtual machines cost-effectively while making sure their data is saved. And second, how to track the costs for the finance department. Let's find the 2 best answers that address these 2 problems. Let's start with option A. This directly solves the first problem of cost optimization and state persistence. The key here is to stop the VM, not terminate it. When you stop a VM, you stop paying for the most expensive parts, the vCPU and RAM. You only continue to pay for the persistent disk storage. This is the ideal way to save money on development machines that don't need to run 24/7. The No Auto Delete flag is also critical, as it ensures the persistent disk holding all the work isn't deleted, even if the VM instance itself is accidentally deleted. So this is a correct answer. Now for option B. This is incorrect because it does the opposite of what's required. Terminating a VM means deleting it permanently. The auto-delete flag would then cause the persistent disk to be deleted along with it, completely violating the requirement to persist state. All data would be lost. Option C is incorrect because the concept of a CPU utilization label for billing simply doesn't exist in GCP. Labels are static key-value pairs, like team backend, that you assign to resources. They are not dynamic metrics like CPU usage. Let's look at option D. This is the standard and best practice on GCP for providing cost visibility, which solves the second part of our problem. You can export all your detailed billing data to BigQuery. Then, by applying labels to resources like VMs and disks, the finance team can run simple SQL queries in BigQuery to group costs and see exactly how much each team or developer is spending. This is a correct answer. Option E is incorrect for 2 main reasons. First, data on a local SSD is temporary and is lost when a VM is stopped, which violates the state persistence requirement. Second, the process of snapshotting, terminating, and then recreating a VM from a snapshot is far more complex and time-consuming than simply stopping and starting it. Finally, option F is incorrect for similar reasons. Google Cloud Storage is object storage, meant for files and backups, not for the active state of a running operating system. The workflow described here is just as inefficient as the one in option E. So, to wrap it all up, the 2 steps you should take are A, to manage the VMs efficiently, and D, to provide clear cost visibility. Question 15. You have recently migrated data to the Google Cloud Platform, and you are ready to connect your on-premise networks to Google Cloud. Review the requirements below and choose the best connection option. The requirements are: * guaranteed network availability and high bandwidth is low. * a private network connection is not required. * custom routing is not required. * Google Workspace access is required. Asterisk and the budget to establish the connection is none. Which option fits these requirements best? A. Direct peering. B. Carrier peering. C. Dedicated interconnect. D. Partner interconnect. Alright, this question is a process of elimination. We need to find the one connection option that fits a very specific set of requirements, with the most important one being that there is no budget. Let's start by ruling out the easy ones. Option C, dedicated interconnect, and D, partner interconnect, are both premium services. They provide a private, high-availability connection directly to your VPC with a guaranteed service level agreement, or SLA. They are expensive and provide a private network. This directly contradicts the requirements of no budget and private connection not required, so we can rule both of these out immediately. Now for option B, carrier peering. This is a service where you pay a partner carrier to get a connection to Google's network. The key word here is pay. Since the budget is zero, this option is also incorrect. This leaves us with option A, direct peering. Let's see if it fits all the requirements. Asterisk, is it free? Yes, direct peering itself is free. You only pay for your own costs to get to one of Google's peering locations. Asterisk, is a private connection required? No, and direct peering connects you to Google's public network edge, which is exactly what we need. Asterisk, does it provide access to Google Workspace? Yes, because it connects you to Google's public services. Asterisk, and finally, does it have a high availability SLA? No, it doesn't, which aligns perfectly with the low availability requirement. Checks all the boxes. Therefore, the only option that fits all the requirements, especially the budget constraint, is a direct peering. Question 16. Your company wants to track whether someone is present in a meeting room reserved for a scheduled meeting. There are 1,000 meeting rooms across 5 offices on 3 continents. Each room is equipped with a motion sensor that reports its status every second. The data from the motion detector includes only a sensor ID and several different discrete items of information. Analysts will use this data, together with information about account owners and office locations. Which database type should you use? Flat file. B. NoSQL. C. Relational. D. Blob store. Okay, this is a classic architectural question about choosing the right database for the right job. Let's analyze the requirements. First, let's look at the data itself. The data source is 1,000 motion sensors. The data velocity or speed is very high. Each sensor reports its status every second, which means we have a stream of 1,000 records being written every single second. This is a classic example of time series data from an IoT application. The data structure is also very simple, with just a sensor ID and a few other pieces of information. So, putting it all together, the database we choose must be able to handle an extremely high write throughput. It needs to scale easily to handle a growing amount of data from thousands of sensors. And finally, it should be well suited for simple data structures that don't require complex relationships or transactions. With those requirements in mind, let's look at our options. Option A, a flat file system, is incorrect. A collection of flat files isn't really a database. It lacks essential features like indexing for efficient queries and can't handle a high rate of simultaneous writes. It would be incredibly slow and difficult for analysts to query this data. Now let's look at option B, NoSQL. This is the correct answer because NoSQL databases are specifically designed for scenarios just like this one. First, they are built to handle massive read and write throughput, which is ideal for IoT sensor data. Second, they are designed to scale out horizontally with ease, allowing them to handle growing data volumes without a loss in performance. And third, their flexible schema is a perfect match for the simple, non-relational data coming from the sensors. Option C, a relational database like CloudSQL, is not the best choice here. A traditional relational database would struggle to handle 1,000 writes per second on a single table without significant tuning and powerful hardware. The overhead from ACID transactions and a strict schema is unnecessary for this type of data and would only hinder the write performance. Finally, option D, a blob store like Google Cloud Storage, is also incorrect. Blob storage is designed for storing large, unstructured binary objects, or blobs, like images, videos, and backups. It is not a database and is not designed for storing and querying small, structured records at a high frequency. Therefore, the only database type that meets all the high throughput and scalability requirements is B, NoSQL. Question 17. A mobile gaming firm is planning to launch a multiplayer version of their flagship game. They are using Bigtable as a database and an application layer running on GKE containers. Since it is hard to predict the traffic, they are planning to use Ingress for load balancing to dynamically scale the application layer. They want to restrict the traffic from the web layer to the application layer only, and not to the database layer. What is the easiest way to achieve this? Create a different subnet for each layer. Use VPC network peering to allow traffic between the web layer and application layer and the application and database layer. B. Create custom tags to identify the GKE containers and create firewall rules using the tags to allow the desired traffic flow. C. Create custom tags to identify the GKE containers and set up routes using the tags to allow the desired traffic flow. D. Create custom labels to identify the GKE containers and create firewall rules using the labels to allow the desired traffic flow. Alright, this question is all about network security within a 3-tier application on Google Cloud. The core challenge is to correctly isolate the different layers using firewall rules, specifically for an application running on GKE. We need the easiest way to make sure the web layer can only talk to the application layer and is blocked from talking directly to the database layer. With that goal in mind, let's evaluate our options. Let's start with option A. This is incorrect because it's way too complex. Creating separate VPCs for each layer of a single application and then peering them together is a heavy-handed solution and definitely not the easiest way. This kind of separation can be achieved much more simply within a single VPC using subnets and firewall rules. Next, let's look at option C. This is incorrect because it confuses the purpose of routes and firewall rules. Routes are like road signs that tell traffic where to go. Firewall rules are like security guards that decide who is allowed to pass. To restrict or allow traffic, we need firewall rules, not routes. Now for option D. This is also incorrect due to a very specific but important terminology issue in Google Cloud. GCP's VPC firewall rules do not use labels to target resources. They use network tags or service accounts. While Kubernetes itself uses labels all the time, the VPC firewall, which operates at a lower level, does not. So you can't create a VPC firewall rule based on a label. This leaves us with option B, which is the correct answer. This is the standard method for applying VPC-level firewall rules to GKE nodes. Here's how it works. The GKE containers run on virtual machines, which are the GKE nodes. You apply a network tag to these nodes. Then you can create VPC firewall rules that specifically target that tag. This allows you to create a rule that says, for example, allow traffic from the web layer only to VMs with the app layer tag. It's a direct and valid way to achieve the required network segmentation. Therefore, the easiest and most technically correct way, using VPC firewall rules, is B. Create custom tags to identify the GKE containers and create firewall rules using the tags to allow the desired traffic flow. Question 18. You set up an auto-scaling instance group to serve web traffic for an upcoming launch. After configuring the instance group as a backend service to an HTTPS load balancer, you notice that virtual machine instances are being terminated and relaunched every minute. The instances do not have a public IP address. You have verified the appropriate web response is coming from each instance using the curl command. You want to ensure the backend is configured correctly. What should you do? Ensure that a firewall rule exists to allow source traffic on HTTP/HTTPS to reach the load balancer. B. Assign a public IP to each instance and configure a firewall rule to allow the load balancer to reach the instance public IP. C. Ensure that a firewall rule exists to allow load balancer health checks to reach the instances in the instance group. D. Create a tag on each instance with the name of the load balancer. Configure a firewall rule with the name of the load balancer as the source and the instance tag as the destination. Alright, this is a classic troubleshooting scenario in Google Cloud. Let's break down the symptoms to find the root cause. The key symptom here is that virtual machines are constantly being terminated and relaunched. This almost always points to a problem with the load balancer's health checks. Here's what's happening. The load balancer sends a health check to an instance to see if it's running correctly. If it doesn't get a successful response, it marks the instance as unhealthy. The autoscaler then does its job by terminating the unhealthy instance and creating a new one to replace it. But the new instance also fails the health check, and this cycle continues indefinitely. So, the real question is, why are the health checks failing even though we know the web application on each instance is working? The most likely culprit is a firewall rule blocking the connection. With that in mind, let's analyze the options. Option A is incorrect. You don't create firewall rules to allow traffic to the load balancer itself. Its IP is already public on the internet. Firewall rules are for controlling traffic from the load balancer to your backend instances. Option B is also incorrect and goes against security best practices. Backend instances behind a load balancer should not have public IPs. The load balancer communicates with them over Google's private network to keep them secure. Option D describes a firewall rule that is impossible to create. You cannot use the name of the load balancer as the source for a firewall rule. The source must be an IP range, a service account, or a network tag. This leaves us with option C, which is the correct answer. Google's health checking systems send probes from specific published IP ranges. To allow these probes to reach your instances, you must have a firewall rule that allows incoming traffic from these Google IP ranges on the port your service is running on. Without this rule, the firewall blocks the health checks, causing the instances to be marked as unhealthy and triggering the reboot loop. Therefore, the first thing you should do to fix this problem is C. Ensure that a firewall rule exists to allow load balancer health checks to reach the instances in the instance group. Question 19. Your company hosts many applications on GCP that each store various kinds of data. The head of data compliance is concerned that if there is any PII, or personally identifiable information, present in the data, it might attract fines if not processed correctly. He asked you to come up with a solution that identifies the PII, classifies it, and anonymizes it if it has to be processed. He is aware of the dynamic nature of the applications and data and is looking for a solution that is easy to manage with minimum overhead. As a GCP cloud architect, what solution will you propose? Choose 2. Use Cloud DLP, data loss prevention, to scan data stored in cloud storage, data store, and BigQuery, and use Cloud Data Catalog to tag PII data. B. Use Cloud Data Catalog to search for the PII in cloud storage, data store, and BigQuery. C. Use Cloud DLP de-identification transformation templates for the datasets that are identified with PII and Cloud Dataflow to de-identify them. D. Use Cloud DLP to de-identify the PII datasets and use them for processing. Okay, this question asks us to design a complete, two-step process for handling sensitive personal data on Google Cloud. The solution needs to be easy to manage and have low operational overhead. A complete process for this involves 2 major phases. First, you need to discover where the sensitive data is. Second, you need to anonymize or de-identify that data at scale. With that in mind, let's look at our options. Let's start with option A. This perfectly describes the first phase, discovery and classification. Cloud DLP is Google's specialized service for automatically scanning and detecting sensitive data types like PII across various data stores. Integrating it with Cloud Data Catalog to automatically tag that data is a best practice. This creates a centralized metadata catalog, making it easy to track which datasets contain PII. This is a correct and essential first step. Now for option B. This is incorrect because it gets the roles of the tools backward. Cloud Data Catalog is for managing metadata. It can't scan the content of files to find PII. It can only search for metadata like the tags that would be created by a tool like Cloud DLP. Next, let's look at option C. This perfectly describes the second phase, large-scale de-identification. Cloud DLP de-identification templates allow you to predefine your anonymization rules, ensuring consistency. Cloud Dataflow is a powerful data processing service. Combining DLP templates with a Dataflow pipeline allows you to build an automated system to process and de-identify the large datasets that were flagged as containing PII in our first step. This is the definition of a scalable, low-overhead solution. So this is also a correct step. Finally, option D is incorrect because it's too simplistic and incomplete. While the DLP API can de-identify data, it's not designed for large-scale, automated batch processing. For that kind of work, you need a robust data processing engine like Cloud Dataflow, as described in option C, to handle the job efficiently. Therefore, the two steps that create a complete, scalable, and manageable solution are A, for discovery and tagging, and C, for de-identification at scale. Question 20. You write a Python script to connect to Google BigQuery from a Google Compute Engine virtual machine. The script is printing errors that it cannot connect to BigQuery. What should you do to fix the script? A. Install the latest BigQuery API client library for Python. B. Run your script on a new virtual machine with the BigQuery access scope enabled. C. Create a new service account with BigQuery Access and execute your script with that user. D. Install the BQ component for cloud with the command cloud components install BQ. Alright, this is a very common problem that developers run into on GCP. When a script running on a compute engine instance fails to connect to another Google service, the issue is almost always related to authentication or permissions. So, our task is to find the correct way to give a script running on a GCE virtual machine the necessary permissions to access BigQuery, following Google Cloud's security best practices. With that in mind, let's analyze our options. Option A is incorrect. The problem is a connection error, which points to a permissions issue, not a bug in the client library itself. While using the latest library is good practice, it won't fix a fundamental permissions problem. If the library were missing, the error would be an importer in Python, not a connection error. Option B is also incorrect. Using access scopes on a VM is an older, less secure method for granting permissions. The modern, recommended best practice is to use granular IAM roles assigned to a service account. Access scopes are often too broad and less flexible. Furthermore, this solution requires creating a whole new virtual machine, which is disruptive and inefficient. Now let's look at option D. This is incorrect because BQ is a command line tool for interacting with BigQuery from a terminal. As part of the Cloud SDK. The problem here is with a Python script using the Python client library, not someone running BQ commands in a shell. Installing this component would have no effect on the Python script's ability to connect. This leaves us with option C, which is the correct and most secure way to grant permissions to applications running on GCP. Here's the process. First, you create a new service account, which gives your application its own unique identity, following the principle of least privilege. Second, you grant this service account a specific IAM role, like BigQuery user, which gives it the exact permissions it needs and nothing more. Finally, you attach this service account to the GCE virtual machine. The Python client library will then automatically use the credentials of this attached service account to connect to the BigQuery API. This is the most secure and correct way to resolve the connection error. Therefore, the best solution is C. Create a new service account with BigQuery Access and execute your script with that user.